Imagine you are handed a notebook filled with decades of airline passengers' numbers, ups, downs, seasonality, and all the unpredictability of real life. You wonder, can we build a model that not only sees these patterns, but also predicts the future? Hey everyone, my name is Alexei, and today I will walk you through a hands-on exploration of Chronos, a modern framework for time series forecasting. Chronos is a family of pre-trained time series forecasting models which are based on the language model architectures. But before we go deep into this, let's have a look at the problem we are trying to solve. Quick disclaimer, I am a software engineer at Google, but everything I share in this video represents my personal opinions and does not represent Google View. Let's dive in. To define a problem, let's have a look at the following airline passenger dataset. This code is not very important for now, but what is more important is the graph. In this graph you see that we have 144 entries. It's a monthly passenger numbers over 12 years. We plot the historical context in blue and highlight the forecast window in red. This gives us a clear view of the challenge. We want to predict the future passenger counts based on the past trends and seasonality. First, let's see what a pre-trained Chronos model can do. Here we load the Chronos tiny T5 model using Chronos pipeline. The from pre-trained method loads serialized model from Hugging Face and has 8 million parameters. Let's use the pre-trained model. We're using the pipeline model and asking it to predict the forecasting window. We feed our historical context and we want to predict the next 24 months of the user airline passenger details. We also ask to generate 100 possible futures for the uncertainty estimation. Let's have a look at the graph. We plot here the historical context in blue. We also plot the target future data. This is the actual data. In green, there is a forecast median. We also have an 80% prediction interval. As you can see, the model forecast closely follow the actual trend, and the median absolute percentage error, MAE, is just a 5%, which is here. Let me quickly summarize what we see here. The language model architecture designed for discrete data and trained using a fixed vocabulary, let's say 32,000. Then use a Tokenizer to convert the raw text into embedded vector. Just using the same approach wouldn't work because we have a continuous numbers, our time series, which wouldn't work with existing language model architectures. The Chronos solved this with scaling and quantization. We got our raw input, continuous values like 10, 20, 15. Then we apply scaling, which normalizes the value so they fit into the specific range. And we used quantization, which maps these continuous values into bins. Each bin represents a token in the vocabulary. In the last step is embedding, where these number tokens are then treated actually like words and converted into vectors back. Let's visualize the binning process. First, we define the bin centers as evenly spaced points between -2 and 2. Then we calculate the boundaries based on these bin centers. Next, we generate 1000 values evenly spaced between -2 and 2 to simulate continuous data. Then, for each value, we determine which bin it belongs to by checking which interval between boundaries it falls into, and then assign it to the closest bin center. We then convert all the original values to their corresponding bin centers, which is where we lose some precision because many values now share the same center. Let me scroll down. Finally, we plot the results. The blue line shows the original values, while the red line shows the bin values. We also mark the bin boundaries with vertical dashed lines and highlight the bin centers with the green dots. So this step process visually demonstrates how continuous data is quantized into discrete bins. Just to reiterate, let's have a look at the bin center at point 0. Now, all the values between -0.5 and 0.5 will fall under the same bin center. That is why I said before that we are going to lose some precision because multiple values will map to the same bin center. Now, armed with this knowledge, let's implement a custom Chronos Tokenizer class that's compatible with the Chronos dataset. We define a Chronos Tokenizer class to convert continuous values into discrete tokens, similar to our earlier binning example. In the init method, we set lower and the upper limit. Then we define the number of bins, excluding the special tokens, We calculate the bin centers and boundaries. Let's go to the input transform method. This method normalizes the data by calculating the mean absolute value for each row, basically each sequence. Then we calculate the bin centers by using the torch bucketize method. It is similar method to the numpy digitized as we used before. And then we offset by the special tokens. And this is needed so that the value tokens start after reserved special token IDs. Other methods in this class needed so we can be compatible with the Chronos framework. But the underlying logic is exactly the same as we saw in previous section where we visualize the bidding process. There is no difference. To test our Chronos Tokenizer class, we create a dummy config which has the configuration parameters for our Tokenizer. We said that the path token would be 0, the end of sequence token would be 1, the model type is sequence to sequence, that's the only one that we have for now. Context length is 100 and the prediction length is 5. We use dummy config to create a Tokenizer. To test the Tokenizer, we generate the sine wave with some random noise. We feed this sine wave to the context input transform Tokenizer to get the token IDs and the scale. Then we feed it back to the output transform to get the reconstructed sine wave. We do this to compare the original sine wave with the reconstructed one. Let's have a look at the plot. We have original wave and the reconstructed wave from token. The original wave represents continuous floating point values with full precision, while the reconstructed wave shows what we recover after converting to discrete tokens and back. So there is a trade-off, and the trade-off is acceptable for forecasting since we prioritize capturing patterns over exact values. Next, let's explore how Rotary Position Embedding works. Unlike traditional positional encoding that adds position information to embeddings, RoPE encodes positional information by rotating hidden states using frequency-based transformations. Think of it this way. RoPE spins the data like hands on a clock. The model can instantly tell how far apart any two tokens are just by comparing their angles. Let's have a look at each method. We start with the init. The init pre-compute the frequency bands, which means that it determines how fast each dimension rotates. The update cache method is actually straightforward. If the sequence length changes, it recomputes the sine and cosine values for each position. And the next method is rotate half. So rotate half is actually a math trick that splits the tensor, it swaps and negates halves for rotary transformation. So this class is just a clever math, but we want to deeply understand why and how it works. So let's scroll down and then dive deep into this. We test the RoPE with three words represented as 2D vectors. One would be on the x-axis, another one would be on y-axis, and the third one would be diagonal vector. What we do here is that we plot the original vector, we apply the RoPE, and then we plot the vector after with the RoPE encoding. We calculate the angle here by deriving the angle using the dot product between two vectors and then getting the arc cosinus. And then we plot the graph. Before the RoPE we have three vectors, one x-axis, y-axis and the diagonal vector. And we can see that the right angle, it didn't move. Then the second vector moved from being diagonal to rotating just past the 90 degrees. And then the word 2 said rotates like more than 90 degrees here. And then the exact values are here. So vector 0, angle between original and rotated is 0 degrees. Angle between original and rotated 57 degrees and 114 degrees. To understand why we have those angles, we can go back to our RoPE implementation and do simple tricks. We're gonna print the inverse frequency and we're gonna print frequency. Because the dimension is low for us for the 2D vector, we can just print the frequency and inverse frequency. I'm gonna rerun it here, rerun our experiment. So what we see here, we see that the inverse frequency tensor is just 1, and then the frequency shape is 0, 1, and 2. So this is our positions. We have 0, 1, and 2. Each position rotates just by 1 radian. So that's why the position 0 not rotated, the next position rotated by 1 radian 57 degrees, and the next position rotated by 2 radians 114 degrees. Let's spend a little bit more time on RoPE. Now we have three 4D vectors. And then we instantiate the rotary position embedding with the D model 4 and the max sequence length of 3, which is the same as we define here. And then we pass our test input through the RoPE to get the output. Next, we call extract pairs for test input and output. And the reason why we are doing it is because the RoPE doesn't apply the rotation to all embeddings using the same frequency. What it does, it applies rotation to embeddings in pairs. That's why when we extract it, we got two 2D pairs, which we can easily plot. Let's have a look at the plot. We have a first pair on a position number 0. When we're on a position number 0, our vectors stays the same, they do not rotate. On a position 1, they actually rotate 1 radian per position, meaning that the position 0 stays the same, the green vector rotates 57 degrees because it's on a position 1, and the blue vector rotates 114 degrees because it's on position 2. And we can see it from here. We see that this is the inverse frequency, meaning that the first dimension would rotate by 1 radian, and the next dimension would rotate by 0.01, which is 100% less than the first pair. If I scroll down, we would clearly see this is the second pair on the position 0 and the position 1. And then we clearly see that they do not move. And the reason why they don't move is because when this blue vector moved 114 degrees, this blue vector moved 100 times percent slower, meaning it moved just by 1.14 degrees. And similar to the green vector moved 57 degrees, so this one moved 0.57 degrees. We can see that it moved a little bit compared to the left graph, but not by much. So this 100x difference in frequencies creates a fast and slow rotation effect. The multi-scale encoding lets the model capture both fine-grained local position, like fast pairs, and a coarse global position, like a slow pairs. Now for the deeper question. Why does rotating vectors help understand distance? To answer that, we're going to run a simulation. First, we set up 128 dimension, meaning 44 pairs of frequencies. Then we calculate theta. It's our frequency bands. Remember, the theta 0 is our high frequency second hand, and the last theta is our low frequency, which moves incredibly slow. We arrange distances, we calculate the angles for every possible distance up to 200. Then we calculate the scores. This line is simulating the dot product between two positional vectors. By summing the cosine for all of these different frequencies, we are measuring how in sync the dimensions are at each distance. And finally to the plot. Distance 0, our cos of 0 is 1. This means that every dimension is perfectly aligned. This is the constructive inference. It's a maximum self-attention. But as distance increases, the curve crashes down. This is because the rotations starting to point in random directions. So the takeaway here is that the RoPE gives us a soft window of attention that naturally prioritizes nearby tokens as a side effect of rotation math. And then this last plot, we have a fastest pair, dimension 0, in blue, and how frequently it changes. Then we have a medium pair, the period is different, it is twice slower. Then we have slowest pair, dimension 63. You see, for us it looks like it's just a flat line. We spend so much time on RoPE here because it's one of the part of the Chronos model. So transformers have no built-in sense of order, they process tokens as a set or batch, but not as a sequence. RoPE solved this by encoding position through rotation. Instead of adding position vectors, RoPE rotates each embedding by an angle proportional to its position. And the clever part is that the different dimensions rotate at different speed, some fast for capturing local patterns, and others slow for tracking long-range relationships. So when two tokens are close together, their rotation stays in sync, producing high attention scores. As the distance grows, the rotations drift apart and attentions naturally decays. Now let's create a Chronos transformer encoder with RoPE. We pass parameters as usual, the D model, embedding size, number of heads, encoder layers, the feed-forward dimension, dropout, and the context length. We instantiate the embedding, and the embedding converts every token to a dense vector representation. We instantiate the Rotary Position Embedding, the one that we spent so much time before. And then we have a stack of transformer encoder layers. Then we have a layer normalization, and then we wrap layer norm and the stack of encoder layers into transformer encoder. And that's all for the init for now. The forward in the encoder is pretty straightforward. We pass the tokens through the embedding layer, token embeddings, and then we apply the RoPE layer to inject the positional information. We feed the positionally encoded embeddings into the transformer encoder using the padding mask to ignore padded positions. And then we return contextualized representation. So the encoder processes the entire input sequence at once, loading contextual representation for each token. We can also quickly test our encoder. So we pass the embedding size of 4K, dmodel 256, 4 heads, 2 encoder layers, and 124 dimensional for the feed-forward network, the dropout, and the context license 128. We generate the test input, and then we pass it through the test encoder, and then we get the output. The input token shape is 228. And then the output token share in 128, 256, which is exactly what we have here. Now for the decoder, it is similar to encoder with some more complex logic. So we create a token embedding here as well to convert the token into the dense vector representation. We create the Rotary Position Embedding RoPE. Then we create a stack of layers with the activation function as a ReLU. We have a layer normalization. We wrap everything with the transformer encoder, but we also need to have a linear layer to project decoder output back to the vocabulary space. So now decoder forward method. We embed the target tokens. Then we apply RoPE to inject positional information using the target embeddings. Then for the target mask, we generate a causal mask to prevent attending to future tokens. Then we pass it, the embedding tokens and the encoded memory through the transformer decoder. And in the final step, we project the output to the vocabulary logits. So the generate method is the most complicated one. We start with the batch of start tokens. And then for each prediction step here, we run it through the forward pass to get the logits for the next token. And then we apply the temperature scaling and top K filtering for sampling. So we sample the next token and embed it to the sequence. And then finally we return the generated sequence excluding the initial start token. We're gonna dive deep into sampling in the next cell. And again, to quickly test the decoder, we're gonna instantiate the Chronos transformer decoder with RoPE. We generate the start with start token. Then we pass it through the decoder layer. We got the decoder output. And then we call generate to have a generated sequence. We see that the decoder output is 2 by 1 by 496. I want you to closely look at the generate method. We are using temperature, softmax, and multinomial to pick up the next token. But what do this actually do? Why don't we just pick the next token with the highest score every time? This is where things get interesting. Let's break down exactly how token sampling works. Switching to tokens. First, we create a fake set of logits for 10 tokens. Logits are the raw scores output by a model before converting them to probabilities. Then we print these logits and highlight the token with the highest value. This is what a greedy decoding strategy would always pick. Look at this selected token, we use the argmax function, and then we print the highest probability. In this code block, we are simulating the greedy decoding. We are getting the logit with the highest probability, and then we append it to our greedy sequence, and then we repeat it for 5 times. You will see in the bottom that the same token would always be picked up, meaning that the greedy decoding lacks diversity. Now let's apply temperatures. We have 3 temperatures, 0.5, 1, and 2. Lower temperature make the distribution sharper, favoring the top token, while the high temperatures flatten the distribution, increasing the randomness. Now to the final loop. So for each temperature, we pick the top 3 token probabilities and sample 10 tokens from the distribution. The output will show how high temperatures lead to more diverse samples, while lower temperatures stick to the most likely token. Now let's see output. We have logits, and then token with the highest logits is 320. The selected token is 2, and then the generated sequence. This is our greedy decoding. We see that we tried 5 times, and every time we pick the highest token with the highest probability. Now for the temperature sampling. With the temperature 0.5, when we sample 10 times, what we see is that the token number 2 appears 67.5% of the times, the token 0 appears 16% of the times, and the token 6 appears 7% of the time. We see that the 2 appears 1, 2, 3, 4, 5, 6% of the times, the token 0 appears 2, and then token 6 appears only 1. Then we see that the unique token is 4 out of 10. When we switch to the temperature 1, we see different results. We see that now unique tokens 5 out of 10. The distribution is flattened. Now the token 2 appears 38% of the time, token 0 18% of the time, and token 6 12% of the time. If we go further with the temperature 2.0, now the distribution is even more flat. Token 2 appears 21% of the time, 0 15 and 12. And the unique token is 7 out of 10. Now to the plot. So it visualizes how language model would sample the next token from logits. So the left plot shows raw logits, with token 2 having the highest value, making it a greedy choice. The right plot demonstrates temperature effect on probability distribution. When we have temperature 0.5, it sharpens the distribution, making the model more confident and deterministic. So token 2 dominates with 60% probability, as we saw before. When temperature equal to 1, it's standard softmax probabilities reflecting the original logit differences. When temperature equal to 2, we flatten the distribution, making sampling more random and diverse. All tokens have more similar probabilities. So lower temperatures produce focused repetitive outputs, while higher temperatures encourage exploration and creativity at the cost of potential less coherent results. Now that we understand all building blocks, tokenization to convert time series into discrete tokens, RoPE for encoding positional information through rotation, the encoder-decoder transformer architecture, and temperature-controlled sampling for generating diverse prediction, it's time to put everything together. In the next cell, we'll create our complete simplified Chronos model that combines all these components into a unified forecasting system. The encoder processes our historical context. The decoder generates future tokens autoregressively using the sampling strategies we just explored, and we will tie the embeddings together for parameter efficiency. Let's see how it all comes together. First, we define the simplified Chronos model with RoPE, which inherits from the PyTorch NN model. In the initializer, we initialize the custom encoder and decoder which supports RoPE. And the key details here is the shared embedding layer. Both encoder and decoder share the same embedding layer. This helps the model to generalize better and reduce the number of parameters. Now to the forward method. We run it through the encoder to get the encoder context. The forward method supports both training and inference. In the training mode, when target tokens are provided, we run it through the decoder to get the output and return the results. When target tokens are not providing, meaning it's an inference, we run it through the generate method to get the sequence and then return it from the forward method. The predict method is just a syntactic sugar. We put the model into evaluation mode and then disable the gradient and then run it through the forward method. When we instantiate our simplified Chronos model, we calculate how many parameters we have and then we print it. We have a little bit less than the 3 million parameters. When I move here, instantiate the Chronos T5 tiny model and count how many parameters we have in all layers, print the result, we have that the tiny T5 model has a little bit more than 8 million parameters. So our model is 3 times smaller compared to the T5 tiny model. We have our model, now we need the data. We're gonna work with 2 datasets. The first dataset is the TS mix. It's a real-world time series datasets with the TS mix-up augmentation. It has 10 million samples and we load both train and validation splits. The next dataset is the kernel synth. It's a synthetic dataset that has 1 million samples. We also load train and validation splits. To understand how our dataset looks like, let's visualize a sample from TS mix. Here we plot the first 200 values from the target field of the TS mix sample. And this gives us a quick look at the real-world time series with augmentation. If I scroll down, we then visualize the kernel synth dataset. So the kernel synth is a synthetic dataset generating using Gaussian processes, which helps us the model to learn from wide variety of time series patterns. So this gives us insight into synthetic data used to train Chronos model. First, we need to convert the Hugging Face streaming dataset into the glued-onto-S format. So this class loads a specified number of samples and it filters out any that are too short and stores them in a list. First, we define a configuration class and we set the key hyperparameters. We use the number of tokens, prediction lengths, context lengths, temperature, and the number of samples. Then we instantiate Chronos Tokenizer class. After that, we create a mixed training and validation datasets. So task mix and kernel synth chosen with equal probability. We have 50% chance to get a sample from task mix dataset and a 50% chance to get a sample from the kernel synth. And finally, we print the number of samples in each split. For the task mix, we have 38k samples. For the kernel synth, we have 50k samples. This is for training. And then for the validation, we have less than 4k for task mix and then 5000 for the kernel synth. Okay, training setup is very simple. First, we select a device for training and move our tiny RoPE model to selected device, ensuring all computation happen in the right place. We then create a data loaders for both the training and the validation using a batch size of 64. We set up the optimizer and the loss function. We use Adam for optimization with the learning rate of 0.001 and the weight decay of 0.01. For the loss, we use cross-entropy loss, ignoring any position with the label of -100. Now this cell introduces a train model. It's a common function which handles both pre-training and the fine-tuning. This function takes the model, data loaders, optimizer, loss functions, device, number of epochs, and other training parameters. So what it does, it has a training phase. For each epoch, we put the model in the training phase. Then we iterate in batches. We propagate the batch through the model. We get the logits. We calculate the loss. We have a backward pass, and then we do optimizer step to update the weights. This function also supports validation. So after each epoch, if the validation data loader is provided, we put the model in the evaluation phase, and then we have a forward path through the validation dataset. Then we calculate the average loss, and then we print it for each epoch. So in this cell, we just trigger the main training loop where we define that we have 100 epochs, validation batch is 50, and the batches per epoch is 1500. And now we're coming to the interesting part. We call evaluate model on airline and pass our airline data through pre-trained model. But instead of generating a single prediction, we run the model 100 times using 1.0 as a temperature and set the top K to 50. So each run produces a slightly different forecast due to randomness in token sampling. We then compute the median across all samples as our point forecast and calculate the 10 and 90 percentile. The function also computes standard error metrics. Its MAE tells us an average absolute error, MAPE gives us a percentage error, and the RMSE penalize larger errors more heavily. So this probabilistic approach is what makes Chronos different from traditional forecasters. It doesn't just tell you what will happen, but also how uncertain it is about the prediction. And finally, let's see the plot. We see here a blue line, it's our context, it's a historical data. And the red line is this what we want to see. The forecast median is the dot green line. Green area is the prediction interval between the 10th and the 19th percentile. Let's think about our results. First of all, our model under forecasting. The model significantly underestimates the actual values, especially missing the seasonal peaks. The peak we have is 500 passengers, but our model predicts around 300. It's also missing the seasonality patterns. So the model captures some variation here, but it doesn't fully replicate the strong seasonal patterns like in the actual target in the red line. If we scroll down here, we see that the mean prediction interval is 80 passengers and the max prediction interval is 188. So the prediction interval is large. It's like 100 passengers, indicating that the model knows it's uncertain. To improve our model accuracy in the prediction interval, we want to fine-tune the model on the actual airline dataset. But we're not going to use the airline dataset as it is. We're going to augment it with some noise. This is exactly why we create airline dataset wrapper, not only to convert it to the glued-onto-S compatible format, but also to augment it with some scaling and adding some noise into the actual airline dataset. We're going to fine-tune the model on the training dataset. This is the fine-tuning, and we see our training clause is crashes down from more than 4 to less than 3.0. And then we're gonna call evaluate model on airline function again to see the results. Now let's look at what happens after fine-tuning. So this purple graph shows that our model after just 20 epochs of additional training on the airline passengers dataset. Look at the dramatic difference. The purple forecast line now moves beautifully with the actual values, capturing the seasonal peaks. And let's look at the numbers. Our mean absolute error dropped from 89 passengers down to 56. It's a 36% improvement. Our percentage error came down from 22% to under 14%. But what's more important is the forecast uncertainty. Before fine-tuning, the model was saying I could be off by about more than 100 passengers, which is basically saying that I'm not confident about my predictions. But now the model is saying that I'm confident within about 55 passengers on average. That's the model going from I'm uncertain to know this pattern, but what's more fascinating is the forecast uncertainty. So before fine-tuning, the model was saying I could be off by about more than 100 passengers on average, but now it's saying that I'm confident within about 55 passenger intervals. So that's the model going from I'm uncertain to I know this pattern. So the model learned the specific seasonality and growth trend of airline passengers data, and it shows in both accuracy and confidence. However, we can clearly see that that's not ideal. We capture the seasonal patterns, but we miss the real numbers. So the real numbers is a bit different, and that's because we have a very small model and then we train it just for the 100 epochs on a limited dataset. What are the key takeaways here? The first, the pre-training alone isn't enough. Our simplified model trained on 2 datasets achieved 24% MAPE, and the model learned general time series, but it struggled with the specific airline dataset. Second, fine-tuning dramatically improves performance. After fine-tuning on airline data, MAPE dropped from 24% to 13%. It's a 46% improvement. Third, prediction intervals tightened. The mean prediction interval width decreased from 148 passengers to 55 passengers, showing increased model confidence. And the last thing, the official Chronos T5 Tiny still outperforms due to more parameters, 8 million versus 2.7 million, and the optimized T5 architecture, and it also training on larger, more diverse dataset. So in this video we learned that building Chronos from scratch demonstrates that the core ideas, tokenization of continuous values, RoPE for positional encoding, and the encoder-decoder transformers work for time series forecasting. Fine-tuning on domain-specific data is also crucial for good performance. I hope that you like this video and see you till next time.